Our project is non-invasive wearable ECG monitor with LED alert of cardiac distress. My name is Victoria Quinones, and we have Lillian Penick and Reid on this project too.
Our motivation for this project came from the fact that heart disease is the world's leading cause of death. One person every 36 seconds dies from this. Arrhythmia, which is an abnormal heartbeat, can lead to different conditions such as heart disease, stroke, or death. Some disorders can include bradycardia, which is the heart beating under 60 beats per minute, tachycardia, which is the heart beating above 100 beats per minute, and atrial fibrillation, also known as AF, which is when one has an irregular and fast heartbeat. These conditions are rare for children and adults up to 40, but 40 and older are at high risk for arrhythmia, and at this time, current models or devices are quite expensive, lack reusability, and do not appeal to everyone, which is why we want to make a device that can overcome these obstacles.
Our goals are to create a device that is portable and is able to detect abnormal heartbeat immediately and in real time, so that the user can get help as quickly as possible. For this reason, the method of knowing there is something wrong or one's heartbeat is abnormal is going to be very clear, for example, using the blinking light of an LED. We want to improve how someone experiencing a potentially fatal condition can get immediate attention and be able to constantly know in real time that they're okay, and we can do this by improving the alert system, signal collection so that it is accurate, making it affordable, and making it reusable compared to existing solutions.
We started brainstorming our solution by looking at 3 different facets of the design. We wanted the monitor to be aesthetically pleasing as we were aiming for a wearable alternative. This meant designing something that was inconspicuous and customizable so the user could wear their look of choice. We also wanted the product to be affordable to both the user and manufacturer. In short-term regards, we wanted it to be a cheaper upfront purchase as opposed to what is currently available. Portable ECGs can range from $200 to $500, so while they can be high quality, they also come at a high cost. Apps can be less expensive but require a supportive device like a phone or watch that is capable of handling the software. Even then, the app alone can cost between $80 to $120, and the quality is often subpar due to the distance from the heartbeat. Finally, we wanted the device to produce quality signal to prevent noise or disruption from producing a false reading. This meant looking into the electrodes used, placement of the device, and filtering of the input. Our final solution was to make a belt buckle design, as it checked all the points above and would fit more users. We considered a watch-like design but discarded it for its unoriginality. We also considered a necklace but chose not to pursue it as it would be difficult for the user to see the LED indication of distress.
Initially, we planned to assemble a full circuit ourselves with a notch filter, low-pass filter, and differential amplifier to process the ECG signal. The differential amplifier is used to reduce common noise from the body. The 60 Hz notch filter is used to attenuate the 60 Hz noise that comes from the wiring in most buildings, and the low-pass filter is used to cut off frequencies above 80 Hz, further reducing the noise. We created a circuit schematic for this using LT-Spice, and we used Tinkercad to test the function of LEDs. Because of differences in voltage requirements for the circuit and the electrodes we initially had, along with wanting to cut down on the size of the prototype, we decided to purchase an integrated circuit board from SparkFun for our improved design. Here are the circuit schematics on LT-Spice and Tinkercad. We initially inputted a sample ECG signal into the LT-Spice simulation just to test the filtering. But we ended up going with an integrated circuit, so this was just another iteration in the design process. This is our physical prototype of the heart rate monitor with an LED alert system. We used an Arduino Uno microcontroller and breadboard to connect the integrated circuit with the LEDs. We first had to solder header pins into the heart monitor module to connect it to the breadboard. The sensor cable allowed for transmission from 3 electrodes, so we used standard bipolar leads in an Einthoven's triangle placement. 2 electrodes were placed on the left and right side of the chest, and 1 was placed on the torso. By placing the electrodes closer to the heart, the signal comes through stronger and with less noise from motion artifacts. This slide shows the Arduino coding used for our prototype, as well as a code that would be used in detecting actual bradycardia or tachycardia. For testing the prototype, the activation of LEDs was set up to be more sensitive to changes in signal, since we were testing on someone with a normal heart rate.
Here are images of our CAD design process. On the left, we have the initial solution having a cardboard box containing the Arduino and breadboard circuit. This will be portable and have LEDs on the top to indicate whether they are having irregular heartbeats, depending on how fast or slow it is going. On the side of the box, there will be places to attach the electrodes and the power source. On the right, we have the final solution, which is a belt device that will have the circuit on the buckle, but small enough to fit there, and have the LEDs at the top of the buckle to let the user know which one is lighting up, depending on their heart rate. Not only will the LEDs be indicators, but the buckle will also vibrate to let the user know of any indications. The electrodes will stem from the belt and the waistline will be the ground. This shows that it will be portable and wearable, and the dimensions of the belt buckle will be around 50 millimeters by 40 millimeters by 12.7 millimeters.
Here we have a diagram to show the demonstration of our model. As stated before, the initial simulation tested the LEDs in Tinkercad using readily available data as the input. This was pretty difficult as we also had to create a filter in LT-Spice to reduce the noise to a readable signal. Upon making the actual device, we were able to incorporate the chip with the embedded filter to use our own heart signals with the skin-tacked electrode pads. Because we didn't have someone available with bradycardic and tachycardic conditions, we used the same healthy normal heartbeat with code modifications to show all LED responses. To do this, we first left the code as written to calculate my heartbeat, which was 64 beats per minute resting, and to show that a healthy heartbeat would produce no light in the circuit as expected. We then modified the code cutoff to say, if heartbeat is less than 64 beats per minute, turn green LED on. This is shown on the left where the green LED is blinking. Again, this is not the correct bradycardic cutoff value, but I myself am not bradycardic, so we set the code to read as such for demonstrative purposes. In the same regard to demonstrate a tachycardic input, we modified the code to say, if heartbeat is greater than 64 beats per minute, turn yellow LED on. This is shown on the right where the yellow LED is flashing.
This is to show the green LED blinking for bradycardia, and this is to show the yellow LED blinking for tachycardia.
The materials and cost used for testing are tabulated here. The total came to $53.84 with our construction alone. The actual prototype would use an Arduino Nano instead of an Uno, changing the breadboard cost to $20.70 instead of the listed $17. Estimating a housing print using thermoplastic at $3.50 per cubic inch would add an additional cost of $5.40 for our 1.55 cubic inch device. This brings the total to $62.96 as shown in the bottom left. Marketing at a 20% profit margin with a sale price of $75.55.
For future versions of the design, we would like to improve on a few aspects. First, we would further miniaturize the device so that it is even more portable and inconspicuous. Using a smaller microcontroller and a cohesive LED unit would help with this. We would also like to connect a Bluetooth transmitter to the circuit so that the signal could be sent to a mobile app and recorded. This app could also potentially alert emergency services, healthcare professionals, or a caretaker. This would also help expedite the process of receiving a diagnosis. A future version could also improve on the customizability of the device using printed designs. The durability of the electrodes could be improved with moisture-wicking covers. And lastly, different alert systems with sound or vibration could be tested for those with visual impairments or if the device is tucked away where it can't be seen.
In conclusion, our goal was to reduce the amount of individuals that die from heart failure. It is important to catch this early on and be able to monitor it in real time. We accomplished this with our device and were able to create a final design that would be wearable, affordable, and reusable. Working to improve this device and adding features mentioned in future work will save many lives and have people have a healthier lifestyle in a way that is easily accessible to everyone. These are our references. Thank you. Do you have any questions?